we can start. So thank you all for joining this session. I must say it's the first time I'm doing such a format with, from my home office and remote with Google Meet. And I will also do everything live, so I did not prepare any videos or fallbacks, so I hope it will all work. If you have questions, just ask them, but please use the chat functionality for that. I guess it's easier with many people if I can then read your questions from the chat and then answer them, or then we can discuss them. Guess that's easier. So then let's start with the presentation, and as I mentioned before, a lot of it will be kind of live perform the things in consoles, and then you will see that. So what is TRex? TRex is a traffic generator. They call it TRex Realistic Traffic Generator. It was developed by Cisco. It's an open source, so basically you can take it and do with it whatever you want, almost. And as a key differentiator from other traffic generators or commercially available traffic generators is it comes as a software package. It's not an appliance, it's just a software that you load on your Linux server. And it has some specific requirements regarding the network interface cards that you use if you need high performance. But other than that, it's a more or less standard server that you can use. Now, you might ask, well, it was developed by Cisco. Why isn't it expensive commercial product? Well, it's just started as a small traffic generator within the team that developed routing software. And they needed something which was faster, better available than the Ixias and Spirents they had. And so they just a few guys started with them, and then more and more people inside Cisco started using it, and apparently the business didn't see a business case with this, so they could make it open source, which is great, not only because we can now use it for free, but also because other companies are now contributing. For example, Mellanox is also using it to test their equipment, and they're also contributing back. So this is great. So what are possible use cases that we can use this software package for? Well, we can use it for testing switches and forwarding performance. For example, what is defined in RFC 2544, this is all this IMIX, traffic mix, and forwarding UDP packets of different sizes. We can also benchmark stateful devices like firewalls, or if we need to do carrier grade net or stuff like that. We can simulate many clients and servers, so generate a lot of different streams, which is also interesting for measuring firewall performance and see how they react to a lot of flows. Of course, it's an ideal tool to generate denial of service attacks, and it has also some, let's say, advanced functionalities, so we can simulate routing protocols, for example, which is a bit a newer development within TRex. And the project is around 5 years old, at least when it was available publicly. So how do you deploy TRex, or where can you actually deploy? You can just install it on a bare metal server, on a Linux server. This, of course, is the option which gives you the most performance. But it's also possible to install it in a virtual machine. Of course, there are some drawbacks because performance is not as big. So on a bare metal server, if you have the the right network interface cards, you can easily reach 100 or 200 gigabits of traffic. This is not possible in virtual machines. And you can also deploy it into the cloud. If you want to measure the performance within your cloud deployment, I especially want to mention Azure here, because Azure, in contrast to AWS, they use Mellanox network interface cards. And you can actually access them from, at least from certain types of VMs, and then make use of the full feature set of TRex. But be aware, traffic is what you actually pay a lot for in the clouds, not only Azure, also Google and AWS. So how does it work? How is the architecture, and why is it super fast? In the left side of this diagram, we see how traditional tools work. I just wrote here iPerf, but it also applies to other tools. If they want to generate a packet, they go through the full TCP/IP stack of the Linux kernel. So there is a socket API where it needs to bind to. There is the full TCP/IP stack. Then there are device drivers, and then we are accessing the hardware, the actual network interface card. Well, this is not bad, but with a setup like this, we cannot generate like 20 million packets per second. Or at least not with all the packet manipulations we need for such a traffic generator. While the Linux kernel is not slow, it has a fully featured TCP/IP stack with a lot of features, and a lot of use cases need to be possible, and people want to use that. So if we just want to generate a lot of traffic, we don't need all the features that such a network stack offers. Instead, we can use DPDK, which is the data plane development kit from Intel. They initially created this development kit, of course, for their network cards. And how this works is the Linux kernel kind of hands over control of the physical network card directly to this application. So that means our application, which is based on this development kit from Intel, now has direct access to the hardware. That also means a lot of things need to be implemented by our software stack, which in traditional models, the Linux kernel would do for us. Now we need to implement them on our own, but DPDK actually includes a lot of these use cases already. And there, with this model, it's not only that we only need to use the features we actually need for our traffic generator. There's also another reason why it's faster that way. There, someone mentioning he can't see the presentation. Is that also true for others? Maybe someone can write in the chat. Okay, seems that other people can see it. Yes, okay, so looks like all others can see it, so looks like nothing I can do now about that. So there's another another reason why using DPDK and using this all just and within my application makes the whole traffic generation faster. And the reason is, if I go through the kernel, there's always a task switch. And a task switch means the CPU needs to dump the content of the registers, load the content of the register from the Linux kernel or from the other application, and this is kind of expensive. If we handle everything in user land in this application, then we don't have these task switches. which saves also a lot of CPU cycles. And during these task switches, we also need to copy the content of the network traffic from one memory space, the kernel space, to user land, to the application. But since our application now already controls the network hardware, this copy is not needed anymore, which also, with this step, also we gain a lot of performance. And actually, the DPDK is now used in many software products that do some networking stuff and need just more performance than a normal Linux or BSD kernel can deliver. For example, the virtualized ASRIX from Juniper is also using DPDK for the forwarding plane. Are there questions regarding the architecture or regarding DPDK? So I'm not a DPDK programmer. Usually, if you use DPDK, you're programming your application in C or C++. And actually, TRex, at least the core of it is written in C++, which of course also helps for performance. Then let's go to the next slide. So how is the lab, my home lab? I'm still in home office, so I'll do all these things now at home, which I demonstrate to you. So the lab that I'm using now consists of a little server, and really it's a small server. It's a Supermicro E308D. It has 6 1 gig Intel NICs, 2 different types already on board. It has 2 times an Intel 10 gig NIC on board, and I added a dual port Mellanox 25 gig NIC to this server. So if you look on the internet what this server costs you, it's around 900 Swiss francs. Then you need to add some memory and an SSD, which maybe costs you another 400, maybe 500 Swiss francs. And if you want a bit more performance with this 25 gig dual port NIC, this costs, depends. You find it for 200 if you buy refurbished, or if you want to buy it brand new, it's between 400 and 600 Swiss francs. And then I have a switch, a small one with 2 10 gig NICs, and I have to test and demonstrate other features, I have a Juniper SRX 300. This is just the smallest firewall from Juniper, so don't expect 10 gig forwarding performance. It's really the smallest one for a really small branch office, but it's actually doesn't produce noise, so makes it nice for my home lab. Regarding the servers that you want for TRex, it's not that you use or can use every server. I mean, it runs on basically any Linux server, but for good performance, you want a supported network interface card. Why is this important? On the slide before, we've seen that now the application needs to access the network cards. So the application or the DPDK needs to provide a driver that supports this, and not all available network cards have a driver that is supported by TRex. Most high-performance Intel network cards are supported, and also Mellanox cards are supported. They're not listed is the Intel i250, but the other 4 1 gig interfaces are also listed on the supported drivers. If you want to go with such a small Supermicro server, There are newer models than this one, but you need to be careful if you want to add additional network cards because not all of these have enough PCIe lanes. So to have enough capacity between the CPU and the additional network cards, you need, at least if you want to go with 2 times 25 gig, you need 8 PCIe 3 lanes. And that's exactly what this little server provides. So now let's have a look how the TRex software on this Supermicro server looks like. All the things I'm doing now is on the command line. I connect through wireless through this Supermicro server. So I hope Murphy is away for today. Let's start with how TRex and actually DPDK sees the network cards. Because for high performance, they are key. So what we see here is all the network cards that the DPDK has detected. And actually, the 4 cards here, the Linux kernel already handed over control to DPDK. We see here, first we have the 2 10 gig Intel network adapters, and then we have the Mellanox network adapters. They are listed twice in contrast to the 10 gig Intel NICs. This is because the Mellanox driver is completely different compared to the Intel one, and it obviously behaves different. And these 6 1 gigabit interface cards, they are actually now under control from the Linux kernel, but I could also use them for DPDK, but I stick to the 10 and 25 gig NICs. TRex has its own configuration file that we need to use to tell TRex which of these network interface cards it should actually use for generating and measuring the traffic that we are going to produce. By default, it's this file, but of course we can define our own. With the same tool that lists all the NICs, we can also auto-generate this config file and then just add if we need something special, but I didn't add a lot. So what do we see here? First, the format, it's a YAML file. Then we need to list which interface cards that we are going to use. And actually, this is the address of the PCI device. In the output from above, we could also see that it's the first part here. The first part here is the PCI address. This is what we need to add to the config file. Then I specify how many cores the software should use. I specified 6 cores. It has actually 4 cores plus hyperthreading, so it looks like the box has 8 cores. In the platform section, we define that there is one thread, which is, so I forgot to mention that TRex is multi-threaded, and you should, with defining how many cores it can use, that also defines how many threads it's going to start, so that you can bind threads to cores to gain the best performance. But you don't need to do this binding. TRex is doing that automatically. You just need to define how many cores, how much of your CPU resources it is allowed to use. So we see we have a master thread, which with ID 7, ID 0, a latency thread with ID 7. So that means to measure latency, it is using a dedicated thread. And this thread also has higher priority over the others, so that the measured latency is as accurate as possible. And then we have our kind of worker threads that actually generate the traffic. And it uses, with this configuration, it uses 6 threads to handle 2 NICs. An interesting detail, measuring the received traffic uses almost no CPU cycles on the main CPU. This is because they offload this functionality to the network card. And this is one of the reasons why they need a dedicated driver, and which TRex can handle much more efficient with while using DPDK compared to using an interface of the Linux kernel. Any questions so far? Okay, then let's continue. Let's start with our first test. We use this little switch with 2 10 gig NICs. I already connected it to the TRex machine, and we just want to generate stateful IMX traffic. Why stateful? This is the first mode that was present in TRex to generate stateful traffic. That means there will also be reply traffic, which matches the initially sent traffic, so that it actually then generates TCP sessions, for example, if it's a firewall that you're going to test. A stateful firewall, of course. So you can see here how which IP addresses I added to the devices, and the actual traffic that is generated has a source or destination address, which is kind of in a net, which looks like a network which is attached to the TRex server. It's this 16/8 or 48/8. And of course, to make this work, we need some static routes, actually only 2. This is now on this layer 3 switch. We see we have these 2 static routes, which point to our traffic generator. Now let's check how the test is defined, this IMX test. So here we are. This is again a YAML file which defines our test. The beginning defines this generator section defines how we are going to address and a few other things, but how we are going to address or which IP addresses we are going to put into the packages. So we say we define a range for client addresses, and we define a range for server addresses. And then the next part defines how the actual traffic is going to look. And for that, we can reference PCAP files. So these PCAP files are really files that you can just look at with your TCP dump or with your Wireshark. That means we also have the possibility to actually capture live traffic in a network and then replay it with that mechanism. We also define, for example, how many connections per second it should do for this particular packet. And, or for example, also the gap between packets. And since we want to test IMIX, we have 3 different sizes of packets. It's a tiny packet, it's a big packet, and one in the middle. This is more or less, the numbers here are not super accurate. I think they diverge a little bit from what is in the RFC, but for our showcase, it doesn't matter. Now let's run this this test. This is how it looks like. We start this TRex binary. And by the way, if you ask yourself, how do you get this TRex binary and where can you find it on your server? It's basically you download a TOR file from the project website, unpack it. You need almost no dependencies to install, and then you just run it. It's kind of batteries included. But all the details you find in the blog I wrote about TRex. You find detailed instructions how to install that on CentOS. So now finally, let's start. So we say you need to load the file that we just looked at. Okay, now we see it does something. On port 0, let's go back to the picture quickly. We have port 0 on a TRex, where we transmit data, and port 0 where we receive data and measure it. And we can see this is true. On port 0, we have out bytes and out packets, and in packets and in bytes for interface 1. But if you look at the total numbers, it's not really a lot. There's 53 packets per second. So the reason for this is now we are just kind of playing what we have defined in this YAML file. But this is not particularly interesting. In most cases, you want some more performance. So for this, we can multiply this. And let's multiply it by 100,000. Since this is a switch, we expect actually that it forwards everything without any loss. You also see it spins up relatively quickly. We are now already generating 3 million packets per second. It's not like it needs a warm-up of 30 seconds or something. It was like 2 or 3 seconds, and we're generating the full load. We are now filling almost the pipe. And we see here in this output that actually we transmit 9.5 gigabit and we also receive 9.5 gigabits, so we don't lose anything. That's also displayed here. Drop rate is 0 bytes, so that means our device under test forwards everything and loses 0 packets or bytes. We can also quickly check what the switch shows us about that. So it has packets. I didn't clear the counters. I should have cleared the counters before. Now we don't see, okay, we can maybe see again that they actually increase. Of course, we can also look at the interface itself. And we should actually see it tells us it's now 95% utilized. And actually, this is also what makes sense if you look at these numbers. So the transmit and receive bits are also 9.5 gigabits. So yeah, that matches. This is always important if you start such a test, that you actually check the counters on the device and to figure out if it actually makes sense, or maybe your traffic generator does something weird, or you misconfigured your device that you're going to test. So it's always important to validate that. What we also see here, it tells us something about CPU utilization. And that's actually these 6 cores that we now allocated to produce and receive this traffic. It uses 90% and of the available CPU performance, and it's generating 3.5 gigabits of traffic per core. Actually, that's not too much. You can go much higher, even on this hardware I'm presenting now. Something else we might look at is what actually does that mean for our little server. In top, we see that we actually have, and I started it with -h, so it displays threads. And here we see all the TRex threads. And in contrast to the other statistics, Linux tells us it's using 99.9% of CPU, each of these cores, of these threads. The reason for that is how DPDK works. With DPDK, we are working in a different mode compared to standard Linux. In standard Linux, the network card receives a packet, or actually a bunch of packets, and then it creates an interrupt which the operating system receives. And then after getting this notification, it actually reads the bytes from the network card and puts them into memory and starts processing them. This is efficient because if there's no packet, if there's no interrupt, our CPU can be used for other tasks. And on a general server, that's what you want. But here, our main goal is to transmit and receive packets. And we are not having interesting business logic in that needs a lot of CPU. So DPDK operates in polling mode. So as fast as possible, it asks the network card, is there a new packet? If there is one, it fetches it, does something with it, and immediately asks, is there a new packet? And because of that, the process or the thread is always busy. And that's why we see this high utilization. But TRex provides us statistics how much of the granted CPU resources it is actually using. Interesting to note so I can stop this now. Interesting to note for stateful mode, it also supports NAT detection. So if you have a NAT device, you can tell TRex that it should figure out if there is a NAT. So it puts some payload into the test packets, and then, well, actually there are several possibilities, but it can figure out on its own, this device that we're going to test is performing NAT and can adapt, so that also the counting of traffic is correct. This mode was the first operational mode from TRex, but it looks like now for stateful features, all the development effort goes into a new mode, which is called advanced stateful mode and has more possibilities. I think with the advanced stateful mode, you can do more or less everything that you can do with this initial mode. But this one is the easiest to start with and see how TRex behaves. Let me check if there are some questions in the chat. No, no new questions. Okay, then next. Now let's look at stateless mode. Stateless mode means we are now not generating traffic which simulates a full bidirectional flow. We're just pushing out packets. Usually that's what you need if you're just going to test a switch, or maybe a router which does only look up to layer 3, maybe for ECMP up to layer 4, but it's not interested in deep packet inspection or NAT or anything like this. Then stateless mode is perfect. Because in stateless mode, that's the mode where you can get the most performance out of TRex. With this little super microserver, I could generate 50 million packets per second. Unfortunately, in my home lab, I don't have a device to test that with, so I reached that with actually kind of a loopback. So I used a DAC cable and directly connected the 2 ports on TRex. But this number, I've found it quite impressive for this little box. Of course, with TRex, with stateless mode, there is also a test definition, and this time it's not a YAML file, but it's a Python script. And it's rather short. They use the Scapy library to give you a possibility to define how the packet looks like. So it's, I would say, readable. You define a source IP and the destination IP. And since we are now going to send packets out of each port of the traffic generator, we need to define, or actually we need something to change source and destination address depending on which interface we're going to send the traffic. Oh, sorry. So this is because for that reason we have this if else to flip source and destination address. And then this is the Scapy syntax. We define an Ethernet frame and then an IP header with source address, destination address, and we define it should be UDP and define destination port and source port, and then it should fill up 18 byte. With that, we will get a packet that is exactly 64 byte. We didn't fill in MAC addresses. TRex is doing that automatically for us. So we don't need to define that. But if we want to, we can. So if we want to simulate or test something with strange MAC addresses, we absolutely can do that. We can fill in every bit that we want. But it's in this configuration a bit different to what we've seen before. Before we the basis of the packet was a capture file, and then we could override some fields like MAC address and IP address or ports. And here we actually define everything in a Python script. There is another difference. Now we first need to start a TRex server process and then connect to it with a client process where we actually then start the test procedure. So let's start a server. And we need to tell it we want it in an interactive mode. So you see it looks very similar to what we've seen before, but no traffic is generated. So now we need to switch to a new console. I'm just using Tmux to open a new one. And then we start a client. There is also for stateless mode a graphical user interface, which allows us to define streams and tests. But for now, let's just stick to the console. So now the client started. It tells us the server is now in stateless mode, how much resources it can use from the CPU, and what NICs it's going to use. And now we start generating some traffic. It's similar to before. With -f, we define the test case, this time the Python script. Our 64-byte test. And we also have a modifier, but this time it's not just a multiplier where we can say, do this, but please do it 20 times in parallel. Now it's much more sophisticated. We can specify, use 100% of what this NIC, what the link gives you, or I now specify, please give me 4 gigabit, generate 4 gigabits of traffic. We can also say generate 10,000 packets per second or something. That's also possible. And to see the numbers, we need this console user interface. And with this mode, we see a little bit more data. So if we start in the global statistics, we see that actually to generate, it now generates 4 gigabits of traffic on each interface. And it only uses 16% of these 6 cores. So there is much more potential. We also see that the device that we're testing now forwards everything. And the queue full is actually an indication if our traffic generator, the hardware, has some issues. So if you go too high and this number counts up, that means either the network card or the CPU or the PCI bus in between, something cannot actually generate enough packets and put it on the wire as we specified. But with this 2 times 4 gigabits, that's not an issue at all. And we also see the receive statistics that on interface 0 and interface 1, we received the specified 4 gigabit. That was to expect. I mean, if we buy a switch, we expect that a switch actually can forward what is in the datasheet, and in this case, they say line rate. Just to demonstrate, now we're stopping this, and we're going to generate 40 million packets per second. This is the maximum, more or less. Okay, a few more numbers after the comma, but that's what you can do with 10 gig Ethernet. I see it needs a few seconds to come up to speed, not too many. And now when we see the statistics, what we transmit, if you check layer 1, it's almost saturated. Actually, we could generate a tiny bit more, but then 10 gig Ethernet reached its limits. And it's no issue to receive this amount of traffic. And of course, our switch just forwards it. We see we have a drop rate of 0 and it's green. So we're good. Any questions? Okay, then I'm going to the next. I'm stopping this test. You see now it ramps down, and we don't need the statistics, the numbers for the moment. So I've prepared one more use case. This time we're going to test with a firewall, and nevertheless we're using stateless mode, and we're going to simulate a TCP SYN attack. Our TRex will send a lot of IP packets with SYN flag set on both interfaces. And we're going to see how our little firewall reacts to that. So now I need to quickly move the console cable to the other device, and I'm back in like 5 seconds. So I plugged it in the ngworx firewall. Yes, very good. I quickly show you how I prepared it. I configured the same static routes and interface addresses as I did before on the switch. So you see we have the static routes for the 16/8 and static routes for the 48/8 to route it back. In addition, since this is a security device, I configured a screen. Screens on ngworx firewalls are measures that actually do some statistics to do something with the traffic. And it's obvious what our screen here is doing. It detects SYN floods, and if it detects a SYN flood, it will drop that. To make it active, we need to attach it to a zone that we configure, and to the zone we also need to add interfaces to actually make this active. So this is how it is linked. This screen configuration, the screen 1 is attached to zone 1, and I added the interface 6 and 7 to the zone 1. And if you look again at our picture, these are the interfaces that we're going to use on the ngworx. Now we need to do some additional work before we start on the traffic generator, because I pre-cabled it so that the TRex now connects with, not with the Intel NICs, but with the Mellanox NICs. So we need to change that in the configuration. For this, I need to stop the running server and edit the config file. Actually, that we could also specify the config file when starting the server port, and we could actually use that to run multiple servers on the same box. So this could be an interesting scenario if you have a server with, like here, multiple NICs, and you want different engineers being able to use it at the same time. So they can then connect to different servers, to different TRex services running on the same server, and you can specify how many CPU resources each of these services is allowed to use, so that they don't interfere with each other. So these are the Intel NICs that we are now not using anymore, but we want to use the Mellanox cards. Actually, if you want to go to 100 gig, Of course, you need a bigger box. You probably need, on this server, RAM is only dual attached. You want more channels, maybe 4. And you need faster PCIe or more PCIe lanes than I have in this server. So in this server, 100 gig NIC would not make sense. But there from Mellanox, it's also available a 2-port 100 gig NIC that, according to documentations I've read, works excellent with TRex. So we changed configuration and we start the server again in the interactive mode. See how it comes up. And now we start again the console. Actually, I could have just let it run. It would automatically reconnect. And now let's start with a SYN attack and see how the device behaves. We also add a multiplier, otherwise it just generates 1 SYN packet at a time. And let's say 1,000, so 1 million packets per second. Now we should not expect that everything goes through, because this is a SYN attack, and actually we expect that the screen functionality drops many of these packets. And on the other hand, this box will not be able to forward 2 million packets per second and inspecting and doing statistics and everything. So we don't expect that it forwards everything. What also looks interesting, that even though we are sending on interface 0 and on interface 1, we actually only receive on interface 0. The reason for that is we don't change source and destination address depending on which interface we're sending with this test now. So that means a certain amount of packets go in or actually leave TRex on interface 0, and the SRX sends them back on the same interface. Now let's look how the SRX behaves. First, look at traffic counters, if it agrees with the measurements from TRex. And we see this the same. We see input packets on interface 6 and 7. On both, we receive around 25K packets per second. The rest is dropped even before because it's too much for this little box. But all that it actually accepts, it puts it outputs on interface 6. And now we also want to see if the screen that we configured actually notices something from our attack. So show security screen statistics for our zone, which is called zone 1. And here we see that it detects the SYN flood. So question is now, what happens if we're going to remove this protection? So let's do that. So we're going to remove this this screen configuration, and then we'll see what happens. So now we need to commit and wait a few seconds, and then we want to see. Oh, that was not what I intended. So we see, interestingly, actually the number of packets that are now forwarded went down drastically. Before we had several thousand packets that actually were forwarded by our firewall. Now it's down to almost zero. Now it goes up a little bit. So first I thought this is not expected, but on the other hand, the reason is quite obvious. Let's see some statistics. So something with my console is not right now. Size is wrong. Okay, what's the issue? Oh, now it's fine again, now that the size matches. So let's see some statistics. And I'm in config mode. And then we should see the reason. We see that since now the screen functionality does not drop packets, everything is inspected by the regular security policy, and it generates sessions. And we now have 65,000 sessions. And this is the maximum this device can perform. So once the session table is full, new packets are just dropped until these sessions are timed out. And that's why we see these spikes here. It goes down, and once sessions or started sessions are timed out, then we can transmit a little bit more packets, fill up again the session table, and then it goes back again. So we see here that this screen feature is really useful, and thanks to this TRex functionality, we can actually test it. Are there any questions regarding this last test that I demonstrated now? Then please just write it in the chat. If not, I'm almost finished. You can also think about questions if you have some. It has many, many more features that we did not touch or look at in this demonstration. So I mentioned before there is a graphical user interface for stateless mode. It also has kind of a graphical editor which lets you define all the properties of your packet, how you want it to look like. With stateless mode, now we just generated one stream at a time. But of course, you can generate multiple streams in parallel. Maybe if you want some quality of service testing and then test how it behaves with different streams, with different characteristics, you can also include some bursts. You can also integrate routing protocols. It comes included with the Bird routing suite. So you're limited to routing protocols supported by Bird. For example, ISIS is not included. You can measure latency. All this telemetry data, for example, the statistics, the live data that we were looking at in the console, you can write them, for example, to an influx database or to Elasticsearch. Actually, you're writing Python scripts with the stateless and advanced stateful mode, so you can do everything. You just maybe if you're writing data, you need to consider how much data are you writing and where are you writing it, so that the data sync actually can keep up with the flood of data. It is also possible to capture traffic, but of course, you cannot generate 100 gig of traffic and expect to also capture that and write it to disk. Because usually with capturing traffic and with the statistics, a lot of this functionality is offloaded to the network interface card, and then you cannot capture it. So you can define some filters of some amount of traffic, some specifications that you want to capture, but it's not the high rates as with the other cases. And then there are many, many more features, like you can emulate some protocols. You can do some layer 7 stuff. If you, for example, if you want to do DPI inspection, you can generate HTTP traffic and also responses and even more. And that was the content of my demo. I hope you found it interesting. And I see we have one question. I read it to all of you. What can Spirent or Ixia do better than TRex? So I must say that I don't have any work experience with Spirent or Ixia. My understanding is that they support more protocols, and if you need to simulate a whole network, let's say you want to simulate, I don't know, like 500 ISIS routers, and on top of that, you're deploying your VPLS topology. This you cannot simulate with TRex. You can generate MPLS packets and send them on the wire, but you cannot simulate an MPLS network with 1,000 nodes so that they really react and send the expected packets. This you cannot do. Maybe there are more differences. One big difference is you pay much less for TRex compared to Spirent and Ixia. More questions? If not, then I thank you all for attending my session, and I'm going to close it now. Thank you.